Welcome to our lesson on moments and moment generating functions. Let's see, what are the moments? If we take the expected value of x, the expected value of x squared, the expected value of x cubed, and so on, these are called the moments of the random variable x. And which moment we're talking about depends on which power of x we're finding the expected value of. The expected value of x to the first power, e of x, is the first moment. The expected value of x raised to the second power, e expected value of x squared, is called the second moment. And in general, if we take the expected value of x raised to the rth power, that is called the rth moment of the random variable x. We've already seen two of the moments that we have actually used in the formulas for the mean and the variance. The mean, remember, is the expected value of x, so it really is just the first moment of the random variable x. And the variance, we showed, can be found by taking the expected value of x squared and then subtracting off that mean squared. So this is the second moment minus the first moment squared. So we can see that if we had a handy way to find the moments, then we would also have a handy way to calculate the mean and the variance. That handy way to find the moments for some random variables is going to be what's called a moment generating function. So for some distributions, special functions called moment generating functions can be defined. A moment generating functions can make it simpler to find the mean and the variance of a random variable. And they can also be used to identify the probability mass function, that's our little f of x, remember, for a random variable. So let's define the moment generating function. If x is a discrete random variable with probability mass function little f of x and support s, then the moment generating function, which we denote m of t, is equal to the expected value of e raised to the t times x power. And if we want to write this as a sum, we'd be adding over all the values of x in the support, e raised to the t times x power, multiplied by f of x. That's the moment generating function, which we abbreviate mgf for x, as long as the summation is finite for some interval of t around 0. If the sum is not finite, then the moment generating function of x does not exist. So not all random variables have moment generating functions. How can we find the moments? If the moment generating function exists for a random variable x, then we can find the rth moment of x by taking the rth derivative of the moment generating function and evaluating it at 0. So in particular, since the mean is the first moment, we could take the first derivative of the moment generating function and evaluate it at 0. And since our variance is the second moment minus the first moment squared, we can find that second moment by taking the second derivative of the moment generating function, evaluating it at t equals 0, and then subtracting the mean squared. Let's look at an example. Suppose that a random variable x has the moment generating function given here. If we want to find the mean of the random variable, that's the first moment. We can take the first derivative of that moment generating function and evaluate it at t equals 0. Here's our first derivative, and evaluated for t equals 0 gives us a mean of 2.7. Now let's find the variance. For the variance, we're going to take the second moment minus that first moment we just found squared. So that's the second derivative of the moment generating function, evaluated at 0, minus mu squared. So we'll take the second derivative of the moment generating function, evaluated at 0, gives us a second moment of 9.9, And then we can find the variance by taking our 9.9 minus 2.7 squared. We can find that the variance is 2.61. The other thing that we can do with the moment generating function, as I mentioned before, is we can actually use it to find the probability mass function. So if the moment generating function for a discrete random variable exists, then it can be used to find the probability mass function little f of x, because if the support s is the values b1, b2, b3, and so on, then the moment generating function, because it's the expected value of e raised to the t times x power, and we're summing over all the values of x in the support, is going to be e raised to the t times b1 power times f of b1 plus e raised to the t times b2 power times f of b2, and so on. So we can see that the numbers that are multiplied by t in the exponent, those are the possible values that our random variable x can take on. And their probabilities are given by the coefficient for e raised to the t times that value. It sounds a little more complicated than it really is to work with. Let's look at our example again. So here's our random variable x we're supposing has that same moment generating function that we were working with before. Now we're looking for things that are of the form f of x times e to the tx. So the first term of this moment generating function can be rewritten. 1/10 is equal to 1/10 times e raised to the 0t power. So 0 is a possible value our random variable may take on, and it will take on the value 0 with probability 1/10. This means that f of 0 is 1/10. Then we move to the second term in our moment generating function. We have 1/10 times e to the t power. This is equal to 1/10 times e to the 1 times t power, which means that 1 is one of the possible values that our random variable can take on, and it's going to take that value with probability 1/10. So our f of 1 is 1/10. If we move to our next term in the moment generating function, we have 2/10 times e to the 3t. E is being multiplied by 3, so that's a possible value of x, and the probability that it takes on that value, 3, is equal to 2/10. So f of 3 is 2/10. And moving to our last term of the moment generating function, we have 5/10 times e to the 4t. 4 is a possible value, takes it with probability 5/10. So f of 4 is 5/10. And that's how we can use a moment generating function to find the probability mass function. That brings us to the end of our video.